The electrolysis of aluminium oxide. Metals are used to make many different products in the world today, but most metals are not found in their pure form, called their native state, instead being found in the form of ores, which are mainly compounds with oxygen. It is necessary to extract these metals from their compounds so that they can be used within products. For metals less reactive than carbon, the metal can be extracted through reaction with carbon in a blast furnace, as carbon can be used to displace the less reactive metal in the compound through a displacement reaction, resulting in the pure metal being separated from the compound. For metals which are more reactive than carbon, such as aluminium, the metal cannot be extracted using a blast furnace, as it cannot be displaced by the carbon because the carbon is less reactive, so another method must be used. This method is electrolysis, in which a molten compound has an electrical current pass through it to separate its ions, which travel to opposite electrodes, the part of the circuit in contact with the molten substance, which is known as the electrolyte. This is the case with the metal aluminium, so electrolysis is used to create thousands of tons of aluminium every year, to be used in various different products. Let's take a closer look at the process.
As you can see, the aluminium oxide, or alumina, is put into the cell and electrolyzed to form aluminium. The 5 blocks in the top of the diagram are carbon anodes, and they have a positive charge. Lining the inside of the cell is another layer of carbon, which is the cathode, and is negatively charged. The alumina becomes aluminium and oxygen. The aluminium forms at the cathode, at the bottom, and is extracted at the tapping hole. The oxygen is formed at the anode, at the top, and diffuses into the atmosphere. The carbon anodes need to be replaced every 28 days because they are eroded through the reaction with oxygen. New anodes are made from recycled parts of the old anodes. The process of electrolysis is very energy intensive, so costs a lot of money, but is worthwhile because the value of the aluminium produced is greater than the cost of the energy due to the unique properties of aluminium, which means that it is highly desirable.
Alumina, or aluminium oxide, is Al2O3. This means it contains 2 aluminium atoms and 3 oxygen atoms. As it is an ionic salt, there are actually billions of each type of atom arranged in a giant ionic lattice structure as shown. For this reaction, we will focus on just 2 aluminium and 3 oxygen atoms. While solid, the compound can't be electrolyzed as the ions can't move, but when the compound is heated up to become molten, it splits into free-moving ions. Because the melting point of alumina is 2072 degrees Celsius, and this would take a lot of energy, cryolite is used. When heated up to only 900 degrees Celsius, cryolite becomes molten, and the alumina can be dissolved in it and will still have free-moving ions. The oxygen forms negative anions, and the aluminium forms positive cations. The positive cations are attracted to the negative cathode, so the aluminium forms at the bottom on the cathode. It is still molten because the temperature is so high. The negative anions are attracted to the positive anodes, so oxygen gas is formed at the top and then diffuses off into the atmosphere.
Observing the reaction in more detail, we can see why the reactions within electrolysis occur. Aluminium has 13 electrons, arranged as shown, with 3 in its valence shell, which is the outermost shell. In order to be satisfied, it has to lose these 3 electrons in order to have a full outer shell. Because there are now 3 more protons than electrons, aluminium has a charge of positive 3, becoming positive cations. Oxygen has 8 electrons, arranged as shown, with 6 in its valence shell. In order to be satisfied, it has to gain 2 electrons. Because there will be 2 more electrons than protons, the oxygens will have a charge of negative 2, becoming negative anions. As aluminium loses 3 electrons and oxygen gains 2, there must be 3 oxygen ions for every 2 aluminium ions. The positively charged aluminium cations are electrostatically attracted to the negatively charged oxygen ions, resulting in the formation of a giant ionic lattice structure composed of the aluminium cations and the oxygen anions, in a ratio of 2 to 3. This gives the compound the empirical formula Al2O3, and this is the composition of aluminium oxide, alumina. When dissolved in the cryolite, the ions become free to move, so are able to be separated. When the current is applied, electrons need to flow around the circuit from the negative end to the positive. So through the electrolyte, the electrons need to flow from the cathode to the anode. The negative cathode is therefore giving out electrons. The positive aluminium cations are attracted to it and receive 3 electrons each. This satisfies them and turns them into aluminium metal, which collects at the bottom of the cell. The half equation for this is Al3+ plus 3 electrons becomes Al. This is a reduction reaction because it is gaining electrons. The positive anode therefore needs to take in electrons. The negative oxygen anions are attracted to it and give it 2 electrons each. This means they have no charge, but are not yet satisfied because they do not have full outer shells. To resolve this, the oxygens bond covalently to form oxygen gas with the formula O2. The half equation for this is 2O2 minus becomes O2 plus 2 electrons. This is an oxidation reaction because it is losing electrons. Because of the high temperature at which this is taking place, lots of the oxygen molecules will react with the carbon anodes to form carbon dioxide and carbon monoxide. This means that some of the carbon is taken off into the atmosphere, and this is why the carbon anodes need to be replaced. The overall reaction takes the form aluminium oxide becomes aluminium plus oxygen. The balanced symbol equation for this is 2Al2O3 becomes 4Al plus 3O2. Due to the fact that all the ions in the reaction change in charge, the ionic equation is the same as the symbol equation.
So, whilst the process of the electrolysis of aluminium oxide initially appears to be confusing, it all makes sense scientifically. It is an expensive process, but there are ways to make it cheaper, as we have found, and it is cost-effective overall. Aluminium is used for many things: cars, planes, cans, and tins, and so on and so forth. So, next time you travel in a car, fly in a plane, or drink from a can, you can be sure you know how it was made.